Now, an oxidation state and oxidation number means the same thing. So I don't want you to think that those are two different meanings. It's the exact same thing. It's just a different way to say it. So an oxidation state tells us the charge of the atom based on how many electrons it has. And so it's really just a way of bookkeeping for us to determine how many electrons something has at the start of a reaction versus at the end of a reaction to see which way our electrons are being transferred. So we're going to look at a couple different rules that are associated with oxidation state. And the first one is that any atom in its elemental form has an oxidation state of 0. So what does that mean in its elemental form? That has to do with standard state, and we talked about standard state before. That means we're at 1 atmosphere of pressure, and we're at a temperature of 0 degrees Celsius. So for instance, hydrogen, we expect to be in the gaseous phase. So if we see H2 as a gas, then we expect it to have an oxidation state of 0. Same thing with if we just had sodium metal, for instance. So sodium as a solid, we would expect to have an oxidation number of 0. So this works for diatomic elements as well as monatomic elements. So anything in its normal elemental state has an oxidation number of 0. The next thing is looking at monatomic ions. So if we're dealing with a monatomic ion, the charge of the monatomic ion is the oxidation number, or the oxidation state. Now, oxidation states, you might recall, can either be positive or negative, and we need to specify that. So make sure that you are paying attention to if something is positive or negative, not just what its value is. So if we were to look at, for instance, let's say the nitride ion, nitride is N3-. So its charge is 3 negative, which means that its oxidation state is -3. So usually the way that we write these charges is a charge of an ion, the negative comes after the number. For an oxidation state, the negative comes before a number. If you write it either way, I won't mark it as incorrect, but I just want you to be familiar with what it looks like. And we could do the same thing with a positively charged ion. If we had strontium, that's a 2+ ion, so its oxidation state would be +2. So we have elements, we have monatomic ions, and so the next thing then is we're going to look at ionic compounds. For an ionic compound, break the ionic compound, and specifically we're going to talk about binary ionic compounds right now. Break the binary ionic compound into its ions. Oops, that should be ions. Now, what does it mean to be a binary ionic compound? Well, binary means it's just 2 elements. And so ionic, remember, is a metal and a nonmetal. So if we were looking at sodium chloride, we know is NaCl. So that would get broken down into Na+ and Cl-. Well, Na+ therefore has an oxidation state of +1 because now it's a monatomic ion. Chloride is a -1 for the oxidation number. So we can break down an ionic compound to determine each individual atom's oxidation state by looking at what it would be if it were in the ion form. So that's for ions. Then we can look at covalent compounds. And for a covalent compound, we have a couple of rules. So I'm just going to create a little bit of a header. So for covalent compounds, we will see that the sum of the oxidation numbers must equal the overall charge of the atom, or sorry, of the compound. The sum of the oxidation numbers must equal the overall charge of the compound. And this is true for any type of compound. It's just that covalent compounds can have any charge, whereas ionic compounds are always going to be neutral. So the sum has to equal the overall charge. We're going to see that when we're trying to figure out what the oxidation numbers are, we can't just look at them in their ion form because it's not an ionic compound. However, that being said, we do have a rule, and the rule of thumb is that oxygen, when in a compound, so not just oxygen gas, but oxygen when in a compound, will have an oxidation number or an oxidation state of -2. If we know that the oxygen is -2, we can determine what the charge or what the state is of the other element in question. So let's take a look at this. For instance, polyatomic ions are considered covalent compounds because they are held together by covalent bonds since they are non-metals put together for most of them. There are some exceptions, of course, like chromate and permanganate, but generally speaking, most of the polyatomic ions are covalent compounds. So if we were looking at nitrate, for example, nitrate is NO3 with a -1 charge. So how can we figure out the oxidation numbers of each element? Well, the general rule of thumb is that oxygen is going to be a -2, straight off the bat. So we can create a mathematical equation to determine the oxidation state of the nitrogen. So recall that the sum of the oxidation numbers must equal the overall charge. How do we determine the overall charge? We look in the upper right-hand corner of our compound. So we have a -1 charge overall. So we need for our nitrogen plus our 3 oxygens. So we have 3 oxygens, each oxygen having a -2 oxidation number equals a -1. Again, we're looking for nitrogen plus our 3 oxygens, each oxygen having a -2 oxidation state. The sum of those two elements has to equal -1 since that's the overall charge of the compound. So we do a little bit of math and we find that the oxidation number of the nitrogen has to be a +5. And like I said before, we could do this with elements or compounds that do not have charges. So for instance, we could look at carbon dioxide. In carbon dioxide, again, we're going to say, well, our oxygen, we know that's going to be a -2. So our equation is going to be carbon plus 2 oxygens, each oxygen having a -2 oxidation state, has to equal a sum of 0 because there's no charge written for CO2. So that makes carbon equal to a +4. So we have oxidation states of atoms in their elemental form, monatomic ions, binary ionic compounds, covalent compounds, and then the last one that we want to do is taking a look at ionic compounds containing polyatomic ions. So I'm going to go ahead and erase all of this because I have run out of room. So again, we're still looking at determining the oxidation state, but now we're looking at it from the aspect of an ionic compound containing a polyatomic ion. In these cases, what you want to do is start with the outer elements first and save the middle element for last. Okay, but we're going to use the same method that we just did. So let's say that we're looking at sodium chromate. Sodium chromate would be Na2CrO4. So oxygen we know is a -2. Sodium isn't going to change. It's going to be a +1. So we can set up our math equation to solve for our chromium. So we have two sodiums, each with a -1 oxidation number. Sorry, +1. I don't even know what I'm saying anymore. 2 sodiums with a +1 oxidation state, plus our chromium we don't know, plus 4 oxygens, each oxygen having a -2 oxidation state, and our overall charge is 0. So we end up with 2 plus chromium plus a -8 equals 0. So chromium plus -6 equals 0. So our chromium has to be +6. And that's how we can determine that. Now, one other trend that I want to point out to you has to do with hydrogen. So hydrogen can change its oxidation state depending on what it's with. So when hydrogen is with a metal, it has an oxidation state of -1. But when H is with a nonmetal, like in acids, it has an oxidation state of +1. So make sure that you are able to note that difference. When in doubt, use the charge from the periodic table, especially if you're dealing with something like the sodium chromate that has multiple elements in it, more than 2. So sodium is always going to be a +1 unless it's sodium metal by itself. So since that is a charge on the periodic table that is stagnant, it's never going to change, we can just automatically assume it's going to be a +1. So now that we have our rules of our oxidation numbers, we can go ahead and look at a reaction, determine what's being oxidized and what's being reduced, and what is the oxidizing agent or the reducing agent. So let's try that out. We're going to look at this reaction where we have magnesium oxide plus iron, and we end up making some iron 3 oxide plus some magnesium. So once this is balanced, we're going to go like this, and our equation is balanced. So the first thing that we need to do in order to determine what's being oxidized or reduced is to find our oxidation states. So go ahead and pause the video, take a second to try and figure out the oxidation state of each of these elements, and then we're going to figure out what's being oxidized and what's being reduced. So I'm going to start off looking at my magnesium oxide, And we ask ourselves, is this an element? Is it a monatomic ion? Is it a binary ionic compound, a covalent compound, or an ionic compound with a polyatomic ion? So this is a binary ionic compound, which means that we just break the compound up into its ions. And that means magnesium is going to be a +2, oxygen is going to be a -2. Then we move over to iron. Iron is in its elemental state. So it's going to have an oxidation of 0. Moving on to iron 3 oxide. Again, this is a binary ionic compound. So our iron has a +3 and our oxygen has a -2. And then lastly, our magnesium is now in its elemental form, so it is going to be 0. So now we have all of our oxidation states, and we need to figure out what's being oxidized and what's being reduced. So let's try and remember what those terms even mean. In order for something to be reduced, it is gaining electrons. And as such, that means we expect for its oxidation number as we go from the left side of the chemical equation to the right side, we expect for the oxidation state to decrease. Whereas oxidation means we are losing electrons. And so since we're losing electrons, that means that we're looking for, from left to right of our balanced equation, for an oxidation state that increases. So one really easy way to remember this, how I was taught it back in my day of school, which I know wasn't really that long ago, but I just like to say back in my day, we had something called oil rig, and that's how we remembered this. So oil is oxidation is losing, and rig is reduction is gaining. And I've heard of several other types of mnemonic devices to help remember this, so whichever one you find most beneficial is the one that you should obviously go with and use for the remainder of this chapter. But I personally like to use oil rig. So I think it's easier to start off by figuring out what is being reduced. Because for something to be reduced, it literally means it is being decreased, or it is getting smaller. So if we look at our elements from left to right in our balanced equation, which element is getting smaller in its oxidation state? And so you should recognize that magnesium is going from a +2 to 0. It is the only oxidation state that is decreasing, so this is being reduced. Then we can look for our oxidation. Again, for oxidation, we expect for the number to increase. So that has to be our iron, because it's going from 0 to +3. In this case, our oxygen stays the same. It stays at -2, which essentially just means that it is a spectator ion and it's not actually important in this reaction. It just kind of watches the redox occur. So we've determined what has been oxidized and what has been reduced. Now we're going to write half reactions. And for a half reaction, that just means that we're writing only the oxidation or only the reduction. So we're just writing half of our total reaction. So we did reduction first, so let's just do that one again. So for reduction, again, we're ignoring the oxygens. So I'm starting with 3 magnesium ions, and I'm going to be making 3 magnesium solids. Now, when we're balancing any kind of redox reaction, we not only have to be balanced based on the amount of each substance, but we have to be charge balanced as well. So over on the left side of our equation, we have 3 manganese ions, each ion with a +2 charge. So if we have 3 of a +2, that means we have an overall +6 charge on the left side of our equation. If we go to the right side of our equation, we have 3 magnesiums that don't have any charge. So overall, this is neutral or it has a 0 charge. And remember that being reduced means we are gaining electrons. So in order for us to balance out a +6 and a 0, we're going to add electrons to our equation. And since they're being gained, they're going to be in the reactant portion of our balanced equation. And so we need to add 6 electrons, which I just write as E-, in order to balance our equation. So now we have stoichiometrically balanced and charge balanced. And that's our reduction half reaction. Now let's take a look at our oxidation half reaction. So here we're starting with 2 irons and we're turning into, again, it's still 2 because we have that subscript, but now it's iron ions. So Fe3+, and we have to look at our charge. So on the left side of our equation, we don't have any charge, so that's 0. On the right side, we have a 3+, and we have 2 of it. So that gives us a 6 positive charge. So again, we need to cancel out that +6. So since this is an oxidation, we're losing electrons. So that's going to put our electrons on the right side of our equation. We're going to have 6 electrons here. Now we have our stoichiometry balanced out and we have our charges balanced out. Now, one way that you can tell that you're doing the problem correctly is if you end up with the same number of electrons in both of your half reactions. Because we can only give and take the same amount. We can't give electrons and only take 2 electrons. We have to be balanced there. So this is a really good way to check yourself. The last piece that I wanted to look at was determining if something is an oxidizing agent or a reducing agent. So we need to remember what that means. An oxidizing agent is the element or compound that is used to help something get oxidized. So an oxidizing agent, 99.9% of the time, is the substance that is getting reduced. Again, an oxidizing agent is the substance that is helping something get oxidized. And it helps that other substance get oxidized by itself becoming reduced. So the oxidizing agent and the reduced substance are the same. So in this case, what's being reduced is the magnesium oxide. So we would say, oh no, so we would say that our oxidizing agent is the magnesium oxide. And so in this case, when you're talking about the agents, you want to talk about the entire compound. And then our reducing agent is roughly the same idea. A reducing agent is a substance helping something else get reduced. And it does that by itself becoming oxidized. So we look at our equation to determine what was oxidized, and we can see that it was the iron, and it was just iron. It wasn't iron in a compound at the start of the equation. So that's our reducing agent. So we have discovered, first of all, how to write our oxidation numbers. And once we know our oxidation numbers, we can determine what's oxidized, what's reduced, how many electrons are being transferred, what the oxidizing agent and what the reducing agents are. So lots of information that we can gather just by looking at our oxidation states.